Hello everyone, we come up with a paper review. The title of today is Impact of Intraseasonal Oscillation on the Activity of Tropical Cyclone in the Summer over the South China Sea. First of all, I think I a little bit introduce about what is intraseasonal oscillation. I show you video to understand with some ease. Mid-Zillion oscillation is a kind of intra-seasonal oscillation I want to tell you. Yeah, this oscillation exists in the tropic area close to equator. I will give you the example about this picture. The blue color in this place means the convective system in this place is very strong, so it's followed by the wet condition, more precipitation and more rainfall. But in another place we have red color means the convective system is weak, even though without convective system, so it's followed by the less precipitation, less rainfall, and even though there is a drought occur. This convective system move from west to east. It starts in the Indian Ocean and across the maritime, Australia, Malaysia, Indonesia, and finally reach in Pacific Ocean. I can show you how it move. It move from west to east, west to east. Yes. It's okay. So because this oscillation has repeated frequency with 30 to 60 days, so called intra-seasonal oscillation. Next, we'll discuss about the inches domain is South China Sea. You can see here. Yes, the South China Sea is a sea in the south of China, east of Vietnam, in the west of Philippines. This is a map for spatial distribution of TC genesis in South China Sea. The TC genesis in South China Sea is occupy 13% of the TC genesis in the northwestern Pacific, and another characteristic of the TC in South China Sea is they have weak intensity because they have short lifetime to exist in warm ocean. Yeah, this spatial distribution of TC genesis is we can see most of TC genesis located in north of South China Sea. Yeah, the data is calculated from May to September, it's peak stormy season. There are several environmental can affect TC genesis in South China Sea, including sea surface temperature, humidity, vorticity, and vertical wind shear. And other phenomenon such as the monsoon, MJO system, subtropical high, and SST gradient, also the El Nino and South Oscillation Index. But in this paper mainly focuses on the intra-seasonal oscillations, includes Mendelian oscillation and quasi-biweekly oscillation. The TC best check data is used to analyze TC position, and the reanalysis data era interim is used to analyze MJO and QBWO propagation. The methodology we use first is we apply the bandpass filter for the original data. Yeah, to take intra-seasonal oscillation. Yeah, this one. So second step, we after we have secondary data, we apply the EOF analysis for secondary data, And after applying EOF for secondary data, we have PC1 and PC2. PC means the principal component. It is two first principal component of EOF. The PC1 and PC2 are used to determine the MJO and QBWO's propagation. Yes, the x-axis is PC1 and y-axis is PC2. The MJO started in the Africa in phase 1, so it propagates into Indian Ocean in the phase 2 and phase 3. It's across marine continent, Australia, Malaysia, Indonesia in phase 4 and phase 5, and finally it's reached Western Pacific in phase 6 and phase 7, and combines the Western Africa in phase 8. You can see this map is combination between the TC genesis number and position and OLR anomaly map. The left hand side is for MJOs. We can see in the phase 1, 7 and 8 is active phase of MJO. So we have OLR is a blue color is in the negative value. It means in this three phase we have convective system is very strong. Yeah. So because the convective system very strong, so we have TC genesis number in three phase 1, 7 and 8 is much higher than the climatology value. In contrast, in the active phase of MJO is phase 3, 4, 5. We have yellow color for OLR. The anomaly means the OLR anomaly is in positive value. It means that convective system in the phase 3, 4, 5 is very weak. Also in this three phase we have TC number is very lower, significantly lower than normal. Yes, it's clear that we can conclude in the active phase of MJO we have more TC genesis active. In contrast, in the inactive phase of MJO we have less TC active. In the right hand side is for QBWO. We have similar result. I don't repeat that. This slide is explanation of physical mechanism. We consider in the left hand side is for MJO and the right hand side is for QBWO. Yeah, we consider three environmental factors includes relative vorticity in this column, vertical wind shear in this column, and vertical velocity in this column. And in previous slide, you remember we discussed about the inactive phase of MJO. This is phase 1 and 8. We have more TC genesis than climatology. Yeah, so why? So we consider three environmental factors. In phase 1, phase 8, we have positive value of relative vorticity. It means we have conversion condition in the low level, and we have low the vertical wind shear. This condition is favorable for convective system. And we have downdraft minus value of vertical velocity is downdraft. Downdraft also, updraft minus value is blue color mean updraft. Updraft also is favorable for convective system. It means that three of these conditions, conversion in low level, the two of these conditions are updraft and low vertical wind shear. Three of these conditions are favorable for the convective system active in the TC warm core. So it explains why in active phase of MJO we have more decisionism than climatology. Yeah. So in contrast, in inactive phase of MJO is phase 2, 3, 4, 5. It's a weak phase of MJO. We have less DC because we have low relative verticity in blue color, yeah, in minus, and vertical wind shear is high in green color, yellow color, and we have downdraft. The positive value is downdraft. The downdraft, high vertical wind shear and diversion in the low level. This condition is opposite with the condition in the active phase of MJO. So this condition is not favorable for TC, for convective system in the TC warm core. So it explains why. And we have less TC genesis in than climatology in the weak phase of MJO. So we can take a similar result for and a similar explanation for QBWO. So I don't repeat that. This is combination between the MJO and QBWO, and we have in the active phase of both MJO and QBWO there are 60 decisionism generated. In active phase of MJO there are only 13. Active phase of QBWO there are only 10, and finally in the inactive phase of both MJO and QBWO we have only a few. Decisionism is 4. So these results strongly show the relationship between the activity of MJO and QBWO and the decisionism. This slide shows a relationship between the MJO, QBWO, and TC motion. And we can see in the active phase of MJO is phase 1 and phase 8. We have TC number moving in eastward is very high, 11. Yes, it's TC moving eastward is mean it move from west to east in this picture, from west to east. Is similar result for QBWO in the active phase of QBWO is phase 3 and phase 4. There are many decisionism is move in the from west to east. Eastward moving is from west to east. Yes, this result shows a strong relationship between the MJO QBWO and the TC motion. It means in the active phase of the intraseasonal oscillation, it tends to push TC move eastward. This explanation is for mechanism. We know the Western North Pacific subtropical high, WPSH. This is very important to drive the TC motion. In the active phase of MJO, phase 1 and phase 8, we have WPSH reaches eastwards, so the east wing is very weak. But the inactive phase of the MJO, and we have because MJO is active and strong, so we the southwest wing is become more stronger, becomes stronger. So it's puts the southwest wing stronger, so it tend to push TC move eastwards. But in the inactive phase is weak phase of MJO, and phase 3, 4, 5, 6. WPSS tend to extend westward, so the east wind is very strong in this case. But on the other hand, the weak phase of MJO, so southwest wind is very weak. So in this case, east wind is predominant rather than southwest wind. So explain why in the weak phase of MJO, the TC tend to move in the westward. The similar result we can gain for QBWO, so I don't repeat that. So these results explain that why the inactive phase of MJO and QBWO, the TC tend to push in eastward. In conclusion, and we have some main point. First, we confirm that MJO and QBWO can affect TC some TC characteristics such as TC genesis frequency, location, motion of local TCs over South China Sea, and the inactive phase of MJO and QBWO, there are more TC generated. The opposite condition is right for inactive phase of both MJO and QBWO. And the final point is really MJO and QBWO is strongly affect TC motion, particularly in the active phase of MJO and QBWO, the TC tend to move eastward. That's all for this paper review. So I hope you can gain some benefit from this seminar. Thank you very much.